Good.
Because there's no like, because their exam is online, so you normally you suspect a machine, you take it, you normally take away his exam away. But this is his laptop, so you might as well take away his laptop and record it.
Yeah.
It is really nasty though. Doing that kind of procedure is really nasty.
Yeah.
Hey guys, I'm gonna take away your laptop for cheating. Low IQ play right there.
Let's give 1 or 2 more minutes for everyone to come.
Because this is the hallway, right?
Yeah.
TA, if you're standing right down there and just stare like a Hawkeye. I think these two are going to probably during the midterm exam, they're like, yeah, I saw a Hawkeye staring you guys down. I know that the TA had to sit all the way back, and I know those two would sit all the way back when we take our midterm. Because I already done it already as a proctor already. So I know these two in the back, they will do the same.
Yeah.
And then me as a team be like, yeah, I know you too. Come like Hawkeyes. I didn't see what proctor, he's like, don't divide them, it's like you like this. You go over here, you go over here. You come out.
No.
That's what my professor did. That's what she did. And you go this side. You go this side. Have fun. I didn't get winter break. I don't find myself my friend. But that's it. I'm going to be grading the papers for the quizzes right now. Let's see how many papers I have to grade.
So I think we should get started, and people will come. How's the second assignment coming along? Have you started working on it? It's better.
It's a little bit better.
It's a little bit better.
Just look at the first questions and
Yeah. Well, I'm glad. Well, I hope things are good. So do come to our office hours. Before I make another announcement, I wanted to highlight something we covered a few lectures ago, and I had a mistake in the slides. I just wanted to correct it and briefly explain what happened. So if you remember when we discussed about the bias variance trade-off some weeks ago, and we derived the sort of these equations, the expression of the error in terms of two components. One was a variance of model G, and another component was the bias of model G. We said how this last term cancels out. And the reason why it cancels out is actually because initially, if you take the expectation over x, this actually does not cancel out because you cannot break apart the expectation into two products. But what happens is that the expectation is taken with respect to a distribution over the data set, D. So what's happened is this variable over the expectation is actually D, is not x. So I added a slide to fix it. So basically, so it's exactly the same thing, but it's spelled out exactly. So here the expectation is taken with respect to a data set. So it's as if, like, we sample multiple data sets together, and we take the expectation over all those data sets of this particular formula. So this is what is happening, and I added a slide to correct it. But this is in the Bishop book as well. So this derivation you can read if you want to read in more detail and to understand the ins and outs. You can, of course, ask in the office hours as well, but you can also read in the Bishop's book. So what is happening is that initially we go through this and take an expectation over the noise variable, which is here epsilon, and then we take a separate. And then we end up with this function g of x minus f of x squared, and then we fix this and take an expectation with respect to this data set. So now we write g in terms of x and d, and that is why. This is how we reach this, basically. Just wanted to, I added this correction in the slides, but just wanted to explain this. You can go through it step by step, and it will make sense. And you can also read it in the Bishop book. It's not too important, so it didn't change the substance too much, because we still get the two terms as before, but just wanted to clarify the expectation with respect to d. So that's why the last term cancels out. Okay. So let's continue with our class today. I hope people can hear me on Zoom, but if not, do write, and my TAs will let me know. Perfect. So we spoke last time about the perceptron. Do you remember? We spoke in the last lecture how we can build. So before we go into this, like how we take a data set that is linearly separable, and we can build an iterative algorithm that finds a boundary that separates the two sets of data. And this was called the perceptron algorithm, if you remember. And I showed you how the training runs. We just do those two small updates over the weight and over the bias, and essentially. Yeah, it keeps changing this boundary up until convergence. So we'll see. We'll see now in this lecture. We'll go over something a bit more generalizable. It's called support vector machines. So support vector machines. It's like it's also a type of method that creates a linear separation boundary between the data. So it's much more general than the perceptron. And we'll see, so actually support vector machines is one of the most foundational methods in machine learning. It has been super popular in the late 90s and early 2000s, up until 2012, up until sort of like deep learning took off. This was the state-of-the-art method for doing machine learning classification and prediction and so on. And you can even extend this framework for doing regression and other things. So it's quite a fundamental concept that we're going to cover today. You'll see it a lot. There's still a lot of research nowadays that is done into these kinds of methods, or even more generally into like what we'll define next lecture as kernel machines. Actually, I should speak closer to the laptop because people on Zoom won't hear me. So you will see in the next lecture how these form a part of a much larger type of methods called kernel machines, because they use something called a kernel trick, and they lift your dimensionality of the data into much higher dimensions. But we'll first cover the basic support vector machines without kernels, and then we will cover next time the kernel machines. A short announcement I wanted to clarify before we start is that we don't have discussion sessions anymore from this week. So from this week onwards, we'll have only office hours. So and I will put that on Canvas as well. We'll highlight to make everyone aware. So this discussion was only for the first 2 weeks. Okay. So we saw the examples last time when we have, for example, two data sets, how you can find quite many different types of boundaries that can separate between the two. And then, of course, like we sort of asking the question, which one of these boundaries, because all of them separate the data perfectly, at least the trained data. But remember, when we're talking about test data, that we might have many other data points that we don't know where they are. Are they going to be here? Are they going to be here? These red ones, what about the black ones? Same, the plus and the minuses. So then we'll have to make a decision which ones of these are we going to favor still. And you can, if we squint at it quite closely, you can see how maybe the blue line is a good boundary. And we discussed this in a few lectures ago. We said, because it preserves, when you project on the data, it preserves some differences. Or if you, so actually we don't do projection here. This is basically one, the reason why we choose this boundary is because it creates like a maximum separability between the two data sets. But that was for PCA, but still, so blue has the largest margin. It has the largest margin between the pluses and the minuses. So, and here by margin, we mean the distance between this line or this hyperplane and the nearest point. So the nearest plus or the nearest minus. So here this is the nearest minus from the blue line. So that will be the margin, that distance. And we saw last time that the way we compute the margin is by doing this w times x plus b, and this multiplied by y, and this will be the margin between a point x, a vector x, and our model. So this is does it make sense why this is a measure of distance for everyone? Let me do something. So just to kind of make sure that we're on the same page. So let me do a short diagram. Do you understand why wx plus b equals 0 and how this is the line, sort of? So it's, if you think of this feature space, again, I'll rotate this a bit. If you think of this feature space in 3D now, so if you do this, so this will be my pluses and minuses, like this. So this is our line. So if we create another dimension z here, then essentially wx plus b is essentially a plane. Essentially a plane in a 3D space. So wx plus z essentially it's like a plane. So I can do like this. That essentially, so we have a plane given by x and y, and we have this other plane which is wx plus b. This is the other plane, like this. So so we have two planes. So we have one plane that is wx plus b, another plane given by x and y, and they intersect in this line here. So this is the intersection. So this line is wx plus b equals 0. Yeah, does it make sense? So so this is how we get that line, and by taking and by multiplying this expression wx plus b with y, and remember y is always in -1 plus 1. So it's just a sign variable. Then essentially what we get is essentially the absolute value in that, because this will be positive here, or this side of the plane will be positive, this side will be negative. So if we multiply by y, it's as if we take the absolute value. So then we measure the distance from the line, from that line equals 0. Does it make sense? Okay. So support vector machine is a classification algorithm that finds the maximum margin separating hyperplanes. So we have what we're going to discuss today is this type of algorithm that finds the maximum margin. So it will try to maximize this margin, this expression, which is the measure of distance. So because we multiply this, which has a sign, with the actual sign. So this will always be positive, and it tries to, it takes the minimum margin and tries to maximize it. So how is it different from Perceptron? Quick question.
Non-linearity.
Non-linearity.
It can model non-linearity.
No, it's actually this form that we're going to discuss at least today will be linear. We will discuss a more extended form of SVMs with kernels, and that will be non-linear version. But right now we're still in the linear regime. Any other ideas? How is that different from Perceptron, from what we were doing last time?
Was Perceptron classification?
Sorry?
Was Perceptron classification?
It was also classification. So Perceptron was also doing working with binary classes. So still same regime, just binary labels.
Did that also do regression?
No, it was classification. So Perceptron was not trying to find the maximum margin. It was trying to find any Perceptron would equally give any of these lines. The algorithm, the Perceptron algorithm was doing the many iterations up until it was up until all the data was linearly separable, and if the data was not linearly separable, it would never converge.
So depending on how your Perceptron iterates specifically, you could end up with any one of them, and they don't.
Exactly. So with Perceptron, you can end up with any one of these lines. With Perceptron, you can end up with a green line. And
Likely you probably end up with a green line, right?
it depends. It depends. It depends on the data. But with the Perceptron algorithm, when it finds a line that separates, it stops. So it doesn't do that's it. It just finds the first line that separates the data and it stops. So here we're in a bit more complex regime. Now we want also to have a maximum distance from any data points, basically. So we now want to be as far away from any data as possible to get a very robust margin that will generalize. So the input are again just to go to the setup, are sets of training pairs, x's and y's. So x is again it's a d-dimensional feature vector, y is a label, y is a binary label, as we showed here. So as in Perceptron. The hypothesis class, when we talk about hypothesis class, we mean all the possible boundaries. So you hear this a lot in machine learning. So all the possible models that in our model family. So this in our case is a set of all hyperplanes, set of all lines. And hyperplane is just a generalization of a line or a plane to multiple dimensions, to more than 2 or 3. So and the output would be the parameters w and b of the maximum margin hypothesis h. So again, w is a d-dimensional vector, b is a scalar. So these are w and b are our parameters that we need to find for this line to give us this particular separating line. So assume we trained an SVM model. How do we do a prediction? If we're given a test instance x prime, the prediction will be wx plus beta plus b, and we take the sign of it. So we take the sign of this, because this will give us wx plus b. So wx plus b, remember again, will give us any value that is continuously positive or negative, because again we're talking about this plane. But when we take the sign, we just snap that to +1 or -1. So it's very simple. If the true label is y, then the classifier will be correct when yes. So this is important. So this when we make a prediction, when we have a wx plus b is our prediction, also called our activation. If we multiply that, if the prediction is correct, then essentially the sign of the prediction of y hat is our prediction, and y will be the same. We have the same sign. So when we multiply them out, so they will always be greater than 0. It will always be 1 if the prediction is correct. because we multiply either -1 with -1 or +1 times +1, so we always get 1. So then the question is, how do we find W and B that specify the maximum margin in a separating hyperplane? So here's some intuition for how we would do this, and this is actually I always find it easier to start with these types of intuitions. So we want to find W and B of the maximum margin separating hyperplane. How do we reformulate that? We find W and B, like which are parameters of the maximum margin hyperplane, such that all the points are correctly classified. We want all the points to be on the right side of the separating boundary. How do we reformulate this? Well, one way is if we can find W and B that maximize the margin, such that all the points are correctly classified. So here we changed, instead of the maximum margin hyperplane, we want to maximize that margin with the closest data point. Maximizing the margin is equivalent to minimizing 1 over margin. It's always the same. So if you maximize f of x, it's equivalent to minimizing 1 over f of x, as long as f of x is positive, and this is the case because margin is a measure of distance. So, and we can also write it, how do we rewrite the last part such that all the points are correctly classified? Well, we can say that y times the activation is positive for all the points, which is what we discussed earlier. So whenever, if the prediction is correct, it will have the same sign as the correct label from our training set. So y times activation will be positive if the prediction is correct. Yes, so. Yeah, so this is a weak condition. Some points can be very, very close to the hyperplane. So we want, yes. So in practice, we want y times activation to be sufficiently positive. So we want actually to be not just like slightly above 0, because we can get numerical errors. We actually want it to be like bigger than a particular threshold. So this is what we're going to do. So in practice, what people do is that we say that y times activation has to be greater than or equal to 1 in general for trainings like an SVM. And this is actually, and now we just reached the formulation. This is how we optimize the SVM, a support vector machine. We have a question. Yes?
Why do we try to minimize 1 by margin, though, like other functions could also be related?
Yeah. You'll see very shortly, it's because 1 over the margin will be equal, will give us a very simple expression to optimize. It will give us the norm of W, more precisely. That's why. So 1 over margin, we'll see shortly. But I'm just kind of like going through a bit. It might seem a bit magic, but it will work out. The math will work out very nicely if we do 1 over the margin. Yeah. So this is what we do. So we find W and B that minimize 1 over the margin, 1 over gamma of W and B, where gamma here is the margin, such that y times our activation, this is our prediction, wx plus b is our prediction, what the model predicts, y is the actual label from the training set, y times the prediction has to be always greater than or equal to 1. This is the constraint optimization formula for the SVM. So let me first make sure. Does everyone understand? Is everyone with me here so far? Yeah? Okay. So then essentially, when we spoke on this already, like, maximizing gamma is equal to minimizing 1 over gamma. If the constraints are satisfied, if these constraints are satisfied, it means all the training data were predicted correctly. So it was able to make a correct prediction on all the training data points for each of them. If one of these is violated, it means the model made an error on the training set. And the variables in the optimization problem, again, are W and B. Just this is a vector of parameters, this is a scalar. Yeah? Yeah, we have a 1 instead of a 0. So yeah, I've already spoken to this. So we have a 1 instead of a 0 to ensure we have a non-trivial margin. So this is more for numerical errors. And this is, this is again, we constrain that all of these have to be equal. This is called the hard margin SVM. We'll see shortly later on in the lecture how we're going to relax this to actually build a soft margin SVM. And then we will allow margin for some errors. But so far, when you have a hard margin SVM, what will happen if our data is not linearly separable?
You won't be possible to complete
Yeah.
the algorithm.
Yeah, exactly. So if the data is not linearly separable, it would not be possible to, it will not be able to fully satisfy all these constraints. So it will not find a solution with a hard margin SVM. We'll have to make a soft margin SVM to enable that. So yeah, in feasible solution, the framework will not yield any hyperplane. So it will not be able to, it will not manage to satisfy all of this. What happens with the perceptron when it's trained on nonlinear separable data? Yeah, in practice, more precisely, it never converges. It will keep iterating until infinity. The training will never stop.
So it would diverge.
Yeah, you can say that also. Yeah, you can say it never diverges, never converges. Yeah. Let's cut some slack. I started hinting just a few seconds ago about how we can build a soft SVM where we basically allow for some of these constraints, and the way we do that is by using something called slack, and the slack is basically some kind of like room for error that we allow the model to have. So for example, if we have a data point here, minus, that is on the other side, and it will be incorrectly classified, then we allow a slack variable, we allow a particular error basically to be taken into account for this particular data point. So then we model this. So for each variable n, we model it with a zeta function, zeta n. This will be our slack, and it will enable us to violate that constraint we had earlier, with that the y times this has to be always greater than or equal to 1. So now we change it to allow it to be violated. We say that this has to be greater than or equal to 1 minus zeta n. So if and zeta n's will always be positive. So if zeta n equals to 0, what happens?
It's hard margin.
It's what, sorry?
Hard margin. Sorry, hard margin.
Speak louder.
Hard SVM, right? That we would
It's hard SVM, exactly. So if zeta n equals to 0, it means we don't need any slack. We don't need the variables are fine. It's basically the constraint we had earlier. If zeta n is above 0, it's positive, and if it's, for example, like it has a high magnitude, it means we enable like a large room for error. And now we change also the optimization function. So instead of 1 over the margin, we also have plus sum over all these slacks multiplied by a penalty constant c. So essentially, whenever we have a non-zero slack, we add that to our optimization to add a penalty. Basically, this is adding a penalty and saying that if you do allow for the slack, then you have to penalize the model. So yeah, we're trying to avoid them as much as possible. So there's one slack variable per training example. Question? Yeah.
If you had like a really extreme outlier, couldn't that one outlier entirely mess up?
It could, but you would have just one slack variable for that one outlier. All the other slacks would be 0, for example, and then and then it would still be, it could mess up, but actually in practice it's quite robust to that that particular, the methods could be quite robust. The hard SVM, for example, could be will never converge, for example, if it's a very bad outlier that is on the other side, and but with this it will always converge, the model, and it will always find a solution. So this is I've been saying this already. So actually let me say one more time. So if zeta is more than or equal to, so actually let's start from the bottom. If the slack is 0, the instance is correctly classified. So let's start from this last bullet point. If this is 0, then the instance is correctly classified. If zeta is between 0 and 1, what happens is that, so the slack measures this distance from this kind of like distance from the outer margin, these dotted margins, because we allow for this particular margin. So zeta being between 0 and 1 means the data point is like this one, like this -1 is like inside these margins. And if zeta is more than or equal to 1, it is a misclassification. So actually, it means that it's actually crossed the boundary. So this minus here, for example, that will have a zeta more than 1, whereas this one will have a zeta between 0 and 1. Yeah, and again, so this is what the slack means. And C, the penalty term C controls for overfitting. So again, this is something we will set a priori. So and the soft margin. So can the soft margin SVM's feasible set be ever empty? Feasible set means that we will actually find a solution or not, and we will always find a solution. The answer is we will always find a solution with this soft margin SVM, no matter what. Yeah. Okay, so one more thing, one important thing I want you to notice always that when we have an SVM like this, which is again a support vector machine as opposed to Perceptron finds a maximum margin hyperplane, it always lies right in the middle, the solution between, for example, this outer dotted line and this other one. Because if it's not in the middle, like for example, imagine if it is like this, if the solution is this, then essentially the model can find a much. It means the objective function was not optimized. The 1 over margin, that margin was not actually like optimized. And if it shifts from here to somewhere further down, it can actually optimize that even further. So this is what is happening. So always it would always be in the very middle. So another key concept is the concept of support vectors. So we were talking these earlier about how we add the slack, how we have the soft margin now. Now we allow for some violations of that original thing by using these zetas and these slack variables. So the vectors for which these constraints are positive, non-zero and positive, are called support vectors. So there will be vectors that lie either on these boundaries or inside this region, all of the regions. So for example, x plus and x minus, because they lie on these dotted boundaries, are called support vectors. And they will be important, very, very important, because these support vectors will give us a solution to the parameters. Remember, we have to optimize W and beta. The solution we'll see shortly how it will be in terms of these support vectors. And they lie on these lines, W x plus b equals 1, W x plus b equals minus 1 respectively. So these two are support vectors, or anything also in between, we'll see shortly. So how do we also how do we find a better expression for the 1 over margin? So let's see. Let's do the following. So in this plot here, we consider a point x1 that is on the boundary. So because x1 is on the boundary, it satisfies this W x plus b equals 0. This is what it means for a point to be on that particular boundary. It has to satisfy that. X, on the other hand, so x plus, which is on the dotted line, satisfies W x plus b equals 1, because that's how we defined it. That's we saw earlier. So this is a point on this particular line. It's by definition. So if you write x plus in terms of x1 plus x gamma, and gamma here is just this margin basically. This margin equals 1. So to translate from x1 to x plus with x gamma, so we just write like that. Then we have x double x plus b equals 1. So from here, we expand x plus into x1 plus x gamma. So W x1 plus x gamma plus beta equals 1. And then we rearrange. So we get W x1 plus b plus w x gamma equals 1. So notice how this simplifies. How does this simplify? What is w x1 plus b? That's 0. It's from by definition. It's how we define, because x1 is on the exact boundary. So this left-hand side, all these two terms are 0. So we get w times x gamma equals 1. And if we take the norm of that, so if something equals 1, then we can also say that the norm of that something equals the norm of the other thing. So we can work with norms. And because w and x gamma are collinear, are exactly actually we don't even have to take the norm. We can write that the dot product between w and x gamma is the norm of w times the norm of x gamma times the cosine, and the vectors are parallel. So then we get this. We get that the x gamma is equal to 1 over norm of w. So we basically and remember, x gamma is the margin we were trying to optimize earlier. So and we were all trying to optimize 1 over margin, or the margin. So basically, so now 1 over the margin is basically just the norm of w. If we do this math, so essentially, so we have to just optimize the norm of w. Is everyone with me? Yeah. Okay. So so this becomes our objective. So instead of this margin, now we optimize the norm of w. And we instead of doing that, we actually optimize normally the norm of w squared, because it's easier to optimize. Because when we do the Jacobian of that, the gradient of that, this will give us a very nice form. And we take 1 over 2. And we have the same static values as before. So this is essentially equivalent to finding the smallest weights possible. So we have to find the smallest weights of our model. Yeah, that satisfy, and well, of course, plus the slack variables that satisfy these constraints. So smallest weights. And I wanted to ask, where have we seen the smallest weights before, this concept of something having smallest weights? Do you remember? Regularization, yes. Exactly. When we were doing regularization in the first 2 lectures, yes, when we were talking about the bias variance trade-off, and we're talking about how we can regularize it, and by adding a penalty on the weights to make them exactly. So we had least squares plus a regularization on the weights. Okay, so we have to find it. So now our problem is basically minimizing the norm of w squared subject to these constraints, and this is a convex optimization problem. So in practice, the function is convex. So basically, this function on the very top, that's a convex function. It has inequality constraints, but that's fine. And there are quite a few solvers that exist in literature. So this is called quadratic programming. So it's quite a whole field, and there's many methods that are known. So this is like a solved problem, and you can use things they call the interior point algorithms. There's like other things, like there's some duality, Lagrangian duality sort of maximizers, and so on. So, but we won't go through those. We cannot cover those in the class. That will be if you take a course in numeric optimization, so you can go through some of those things. But I want you to know that there's off-the-shelf solvers to solve this problem. But what I think we should go through instead is some. We can reach the solution analytically, basically. So we'll see how for SVM we can actually find an analytical solution with what we'll call with the Lagrange multipliers. So we'll go through that right now, which I think will be much more interesting then. And this form on the very top is called the primal form. It's what we call normally a primal form. In many optimization problems, in particular, there's something what we call a dual form. And some of you have any of you seen a dual form before for any particular problem? So it's essentially a way. It's a way to recast the problem, to rewrite the problem in a different way. That when you optimize, you get a different optimization problem, but it will reach the same solution. It's guaranteed to reach the exact same solution, and that will be called the dual form. And there's a whole new theory on this, but we won't cover this in our class, but I will show you how you reach the dual form for this particular problem. So, so this is how the dual form would look like. I'm just showing you the first, and I'll show you afterwards how we reach here. So what we will do, instead of minimizing what we saw earlier, like that like the norm squared, now we maximize. So it always flips the sign. So we always do, instead of minimization, with the maximization of something that you see here that looks like m transpose xn. This looks like a covariance term. It's the covariance between data point m and n multiplied by their labels and times some weights. So these alphas are weights for each of those data points. So we have to find some alphas that maximize this, subject to alpha times y equals 0. So so these alphas will be some sort of weight that we will wait for each training instance. And intuitively, what they will mean in this dual form will mean how difficult it is to classify that particular instance. So it will be some kind of number that intuitively will tell us that. And the whole thing is, if you do optimize this particular form, it will give you the exact same solution. So let's see. So and once we have alphas, W and beta can be computed as follows. So W will be just a weighted sum of the vectors multiplied by their labels multiplied by these alpha weights. This will be W. And beta will be something else, which is sort of like an average between the minimum and the maximum of WX's over the Y's. But forget about B for now. Just look at W. So notice again what I showed earlier, that W becomes the linear function of alphas. So actually our solution will be a linear function of our vectors. So this will be, so W is equal to, again, x's times the y's are the labels, and multiplied by these alphas. And what will happen is some alphas will be 0. A lot of alphas will actually be 0. We'll see shortly. And if they're 0, it means they don't contribute to finding the solution, W. It will only be a few vectors that will have alphas non-zero, and those will be those support vectors that we saw earlier, if you remember, that lie on the dotted lines or inside the dotted region. And the reason is, we'll go into a bit more detail, but essentially alphas satisfy the KKT conditions, the Karish-Kuhn-Tucker conditions, which are basically like a generalization of the Lagrange multipliers when you have inequality constraints. Have any of you seen KKT conditions? A bit. So essentially, actually, these are really, it's really, they're really fundamental. We won't cover them in the class, but we'll using them a bit here. So one of the conditions in KKT is that the alphas multiplied by 1 minus the activation times label has to be 0. So in this case, either alphas are 0, or in which case the vector is not a support vector, or if its alpha is non-zero, then this has to be 0. So that means this is a support vector. This is exactly on that boundary, so or inside the region. So when can alphas in case instance not be 0? So if alpha is non-zero, then this has to be 1. The activation times the label has to be 1. So then they have to be the same sign. So the prediction must have been not only correct, but also be exactly on the boundary. So for these vectors, for x plus and x minus, that's when alpha can be non-zero, and we'll see shortly. So these are called support vectors. They support the margin, and these are the only vectors that give us a solution. These will be the only vectors, x pluses and x minus, that will give us the solution W. The solution W will be only a linear combination of these two vectors. It won't matter. The rest of the pluses and the minuses will not matter. For example, in this example. Does that make sense? Yeah. Okay, so let's take a 5-7 minutes break and we'll continue afterwards. And we'll also do a quiz. Yeah, you have a question. Okay, so let's go question.
Privately, like a first.
Okay, why don't you come afterwards? Yeah, okay. So let's take a break now and yeah.
So my main this is like the W form. Do you have any like example problems for those formulas? I just want to know. Just wondering because this is kind of like more like a linear regression.
What do you mean by
Like I was just wondering if there are like any example of it because that's just
an example?
Yeah.
Like the one on the right, like the graph on the right. That's an example.
Just know that it's like kind of like a linear regression. I believe.
It's not, I know. It's not. Don't think of it as a linear regression because the problem is a classification problem.
Okay.
It looks like
Oh.
like a regression line, but it's not a regression line. Yeah.
Oh.
It's just a boundary, and everything that is above the line will be classified as a plus,
Oh. So just
and everything below the line
okay.
will be classified as a minus. So it's a classification, binary classification problem.
Never heard of it. That's very interesting to know. And
Mhm.
what's with the middle line? What's that?
The middle line is a main boundary.
Main boundaries.
That's a gap in between. That's the gap where the support vectors will lie. All the support vectors are either on the dotted line or inside that dotted region.
Do you know what chapter I can refer to that?
So look in the book, the Bishop book on SVM support vector machines. They explain quite in detail. But you can also come to the office hours and we can go to this again, or ask questions. You'll have to implement it also in the assignment soon.
Because I kind of
Yeah.
remember.
Yeah. Yeah.
I
Yeah.
kind of.
It's not hard actually.
It's like.
Or work with it. You'll have to call some functions. That you see.
Constant means slack variables, right?
Sorry.
In soft margin, we have the slack variables.
Yeah. Yeah.
So, like, it will be different for each data set, each data point. So,
Exactly.
how do we like find it? Like, how do we clean it?
I'll show you. I know. Yeah. So one way though is. So one thing I want to say, if you have a problem like this, also in general, there are solvers. You can solve it with a Cortex solver. So actually, like even if you don't have an analytic solution, you can always give it to a solver, and they will solve it for you. Like things like nonlinear, like even a nonlinear optimization. But this is even like more. This is a quadratic problem, so there's even more faster solvers, like the interior point method. There's a Lagrange method, active region. I think another one is called. There's a few. You're like, anyway, the whole thing is, you can put it into a function and you can optimize it for you easily. This is hard, and for soft margin. Yeah. It's the same. It's basically with the slack variables. You again put it to a solver, like you. This.
Our optimization variable is W and B, right? Is our slack variable also a
Yeah. So slack, you have to also find solutions for slacks. You have to find a solution for each of these zetas. Yeah. You have to find. So now you have to find. You see minimum W, beta, and Z. Zeta.
just a margin formula, right? It comes with a numerator. How can we simply add it to So when we calculated that to maximize the margin, we can minimize the inverse of it. So at that time, our this slack variables, it was on the right side, right? So we can't simply minimize the numerator of that. So basically, we want to maximize gamma plus that term, right?
Yeah.
So when we
How do you do those constraints? You mean like these constraints on the? How do you do these?
no,
Oh.
that is fine. What I'm saying, our when when we introduce this slack variables, so our margin will become gamma plus c times of this, right? Margin I'm talking about, not this.
On the left or on the right? When do you look on the right? Oh no.
Gamma plus slack variables, this term. Gamma plus c times this slack variables, that is our margin, right? Original margin. We want.
That's the 1 over gamma is the margin.
No, margin is gamma.
Sorry, my gamma is the margin. Yes, 1 over the margin. Yes, yes, yes.
This is our margin for soft margin, right?
Yeah.
Soft margin case.
Yeah.
So if you want to minimize it, so we can do the inverse of gamma, but why we simply adding that other term? Since we want to minimize the whole thing.
Yeah, yeah, because that term gives you an error. That's a penalty. You have to add it because
There is
it's.
a optimization variable over there also, right? That slack variable. So we can't simply add, or can we do?
You
it?
can,
Yes,
you
I
can,
know.
you can. Yeah, yeah, yeah. So when you. Yeah, yeah, yeah. This is basically. This is the. I know that this is a soft margin SVM. It allows for errors, and in the errors, like the zeta will be above 1, and that will give you an error. And if the zeta is between 0 and 1, it will be in that critical region, but still correctly classified actually. So you can do that. You can do that. You add what it means that you optimize the margin, but you also add the penalty. You want to have a low penalty. You also optimize the penalties to be very low.
Yeah, but we want to minimize the penalty as well, right?
Yeah.
So, but
Yeah.
in our margin term, that is addition, right? So if you want to optimize the, we want to minimize it, we have to take the inverse of whole thing, not just one term.
No. I know. No, you don't do that. No, because it gives you a solution that that's weird and doesn't make sense. Yeah. No, yeah. This comes from the KKT conditions. A lot of this, like, so in a bit more, I can give you a bit of the background of how way this kind of comes, but it's too much to kind of cover all of this. Like, essentially, Lagrange multipliers, you apply them when you have an equality constraint. With KKT, with Karosh-Kuhn-Tucker conditions, you apply them when you have an inequality constraint. And inequality, you can do both. So it's a more generalized than Lagrange. So you can deal with both equality and inequality. It's like an extension of Lagrange multipliers, and in that case, you get some variables mu that are kind of like slack variables for the inequalities, or zetas. Here there will be zetas, and you essentially end up like adding them as a penalty. You add in Lagrange multipliers, you add the lambdas. You remember, you add the lambda times that, and that's the penalty, because you have to add the penalty for inequality is not obeyed, and you do the same for the inequality. So that's why you add it like this here, and you don't add it as this is the objective function, but you don't add it inside the 1 over. Yeah, it's I know it's a lot to kind of you cannot go through KKT, like you have to take a numerical optimization class, but yeah. For example, another way you can optimize sometimes is when you do these quadratic problems is if you do like a matrix decompositions, for example. We were talking a bit about eigenvalue decomposition in SVD, but there's some other kind of decompositions you can do, like, and there's a decomposition called LU decomposition, for example, that can be used to, you can decompose a problem, you can optimize like that, and it gives you an analytical solution very nicely in terms of that. So you can use those kinds of things as well. It's, decompositions, matrix decompositions for optimizing this. Yeah.
With SVMs, are there multiple solutions that we can come to that all like have the same optimization, or is there just
a very good question. With the soft margin SVM, just one. With the hard margin, if you have a solution, then it's also just one. What can change, we'll see next time when we do kernel machines, is if you change to different kernel, you can do, then you can get different solutions. Yeah. You'll see. You'll see. Yeah, but it's a very good question. Very good question. Yeah.
Is that like a?
Yeah.
I heard that back in my introduction to optimization class. I don't really see this one. Actually, I think this is like a more of a different one because when I took the introduction to optimization, we've only been introduced to like the big M method, and then I think some.
What method?
Big M.
Big M.
And then I think we've been in I remember the big M method, and there's like I kind of forgot the other concept, but I know the big M method.
Yeah. You do.
Is this one of the
I think you definitely you didn't cover KKT and Lagrange multipliers.
No, because it's not part of the introduction.
Got
to
it.
optimization
Yeah.
class.
Yeah.
It's like an undergraduate, but it's like advanced class.
Yeah, makes sense. Yeah, so you would do in the optimization you would do like things like stochastic the gradient descent. You would do like conjugate gradient methods, like to optimize functions like with a Hessian, with the first order, second order conditions, all of those.
I did not really heard
Yeah.
of first order, second order. Exactly.
Yeah.
That's like for like graduate. That's like
Yeah.
Like a different one. Because then the induction one would be introduced to like the big M method, kind of a little bit like this. I don't remember exactly. I don't remember this one.
Yeah.
How much do you emphasize like the little bit of the introduction to optimization, like the big M method and
It's I don't know that. I don't know what that is actually. I don't.
know that?
No, I don't know that.
I kind of familiar with that formula.
Right.
You explained the min WB.
Z.
Yeah.
Oh. So you have W and B give you the line, the separating line. This one, W in B equals 0. That's the equation. Zeta are the slacks. Zeta allow for errors.
Oh, okay. That's for the error and that's for the line.
Yeah.
Okay, makes
Yeah.
sense.
And they're equivalent. That is equivalent to that. Yeah. So.
Oh yeah, I heard of SVM. Yesterday.
Yeah. Okay, shall we continue? So for the second part, I'll go through the SVM algebra, and we'll do a quiz at the end. So so essentially, these are slides from David Hembold. So and I'm giving him credit. So essentially, he used to teach this class some time ago, and he has some very nice slides for SVM algebra. So I'm using his slides for going through the derivation. And this will be short. This will be around 10, 15 minutes, but it will help you understand where that comes from, where that dual form comes from, and how do you optimize it. So, and then we'll do a quiz at the end. So let's get started. So again, let's remember the context. We're given a data set of x1 of feature vectors x1s and labels x's and y's. Y's are binary. X's are d-dimensional, and we need to find a vector w and intercept b such that the sign of w times x plus b equals to the y. So y is our label. This is the activation, wx plus b. This will be a continuous number. When we take the sign of it, it has to be, it will be +1 or -1. They have to match. So we want to maximize the minimum margin, but or sort of like, remember how we saw how this y times that is the margin. It gives us the margin. So the minimum over I takes us the minimum margin out of all the margins between all the data points. So these distances among all the y's to the line, or all the x's to the line. And then we take the vectors, we do a maximization of w and b over the minimum margin. So we have to find the optimal w and b that minimize this. So we take the minimum margin, basically. That we have to maximize the minimum margin. So in general, these problems when we do a max and a min are not well defined, and they're a bit tricky to work with. But we'll see very shortly. I won't explain these, but because it's not necessary actually. So we saw how this is equivalent to minimizing the norm of w subject to this, and this is also equivalent to minimizing over w and b the norm squared of n times 1 over 2. We will see why, because again 1 over 2 we saw earlier in other examples in previous lectures. It cancels out when we do the gradient with the exponent here. So that's why we do this. We minimize 1 over 2 times w squared, subject to these constraints, inequality constraints. And so this is our original problem on the very top. Now, the primal problem, when we encode with constraints, we essentially, again, we add to the optimization function, we add these slack variables, and this comes from the KKT conditions. So the formally where this comes from is from the KKT, where it's the same as adding the Lagrange multipliers. If you've seen the Lagrange multipliers, you add. It's like this is a variable, that a penalty term, times exactly this condition here, 1 minus that. We multiply this by a penalty, and if alpha is, if this condition on the bracket is not satisfying this equation, then alpha will be positive. Otherwise, alpha will be 0. So we optimize. We do a min and then a max. And with the dual problem, what we do, we basically flip them around. So that's how we get a dual problem. We flip around the max with the min. And again, we're not going into how or when you can do that. There's something called the min-max theorem, which allows you to flip around the minimum and the maximum, basically these operators. There's something called the min-max theorem that you can do that in certain conditions, and that tells us more about when we can flip them. But essentially, that's how we get the dual problem. We flip these terms, and then we get and we get a Lagrangian, and we write the Lagrangian in terms of 3 parameters, w, b, and alpha, which is simply this thing inside the big brackets. We write it like this. This will be the Lagrangian. This is, I hope so far we're mostly familiar with Tebetry, at least with Lagrangian. I hope you have seen this before. Have you? Have some of you? Roughly? Okay. This is how you write the Lagrangian, and essentially we want to optimize this. We want to this becomes a new objective function. It becomes a new objective function that encodes automatically the constraints. This is what Lagrangian is, simply that. And how do we optimize a function? Yeah? Gradient. Exactly. First order conditions. We set we compute the gradient and set it to 0. We always do exactly the same thing. So now we have a Lagrangian, which is and we do exactly the same. We compute the gradient of this whole thing and set it to 0. There's something called strong duality. I'm not going through that. But again, the idea is we have a Lagrangian here, a function that is in terms of 3 variables, w, b, and alpha. And we differentiate this L with respect to w and b. So what do we get if we do the differentiable, like if we do that? We apply a bit of matrix calculus, but don't be too scared. Essentially, this is w times w. This is w squared. So if we do the derivative of that, just think of it as a scalar almost, although it's not a scalar, it's a vector, but it's like a w squared. So this becomes 2w over 2, which is this w. So this is our w. What does the derivative with respect to this become? With respect to w, so we get this term wx plus b with respect derivative with respect to w. What is it? It's just x, right? Yeah, and then we multiply by y, and then we multiply by it's minus y exactly, and we multiply by alpha, and this term cancels out. The 1 cancels out, so we get x times y times alpha with a minus sign. So that's the derivative. So with respect to w, and with respect to b, the same thing. Now this becomes 0, and we have just here b times minus y times alpha. So b cancels out, so we just get minus y times alpha, which is this term. Yeah. So we always do the same thing. We calculate the gradient and we set it to 0. That's how we solve it. And now we have a Lagrangian. So. And the only thing that we have now here, again, with those of you who are not familiar with Lagrangians, is that we added these extra terms which encode the constraint that we had initially, because we had those constraints that we wanted, these constraints that we wanted them to hold. So this is it, and we set them to 0, right? So we set these to be 0, and that's how we get w. So w is just the weighted sum over the vectors multiplied by their labels multiplied by the alpha variables. So that's how we got it. And we also get that the sum of alphas times y's is 0. So actually you can think of it that each vector x has some weight, alpha I times wi, and the sum of those weights have to be 0. So again, this is interesting. This is exactly, this was super simple, right? We just got a solution, analytical solution to an SVM, right? With the KKT conditions. So w equals to this means w is a weighted sum of examples, also like in Perceptron. This equals 0 means that positive and negative examples have the same total weight, and at the optimal condition. The KKT conditions imply that for each constraint term, so these alphas multiplied by this whole thing has to be 0. So either alphas are 0 or this is equal to 0, which means that y times the activation has to be 1. Which means they're exactly on that boundary, on that support. Keep in mind we're still in the hard SVM. This is a derivation for the hard SVM. This is not using those slack variables yet. We're just having a derivation for a solution for a hard SVM. So without any zetas. So when alphas will be non-zero, those will be that x will be a support vector, because alpha is non-zero means this has to be 0. So that means there's 2 boundaries here. Let me do them. There's like a boundary here, and another boundary here, and there would be some vector x here that will lie on the boundary, and some vector minus that will lie on this other boundary. So like that, and W will be a weighted sum of only these boundary vectors. So how do we? Let's actually plug in the Lagrangian, our solution. So what do we get if we plug in this? So for W we plug in what we got, the sum over I over alpha I yi xi. So we get this squared. And so W times W literally becomes this times that, which becomes sum over all pairs I and j of alpha I, alpha j, yi, yj, xi, xj. And if we plug them in here on this side, we get that alpha I times yi times all of this equals to all this stuff. So we have alpha I, these are basically the w's times the x. So we get the same thing. We get like the sum over all i's and j's of alpha i's, yi's, xi's, xj's plus b times this. And we know this is 0 from the condition earlier. We know from this that the sums of alpha i's, yi's are 0. So we use that here. And that's how we rewrite. So if you rewrite it, we're using all these things, all these derivations. Now we have the sum of this plus this plus that b basically. So if you rewrite it, we basically get 1 over 2 times all the sums of alphas, y's, and x's, plus the sum of alphas minus the sum over i's and j's of the same thing. And this cancels out with this 1/2. This is a full unit. This is a half a unit. So what we get is the sum of alphas minus a half of this thing, basically, because this cancels out with that. Do you see? Is everyone following? Okay, so this is, if you remember, this is exactly the dual form that I had in the slides earlier. This is exactly how we were saying we maximize the alphas. We maximize over alphas this particular form. Over alphas, alpha i's minus alpha i's, yi's, xij's. This was exactly the dual form we had in the slides earlier. And this is how we derive it. So this is what the slide is saying. So we have this substitute, this dual form over alpha. So we maximize this over alpha, which alphas are bigger than 0. It's a quadratic problem. It can be done numerically. So, and from alpha stars, these will be the non-zero alphas, the alphas which will be non-zero. We compute the support vectors. So which will be, no, we compute the solution, sorry. So the solution is a linear sum of only the support vectors. Because for the other alphas, they'll be 0, so they won't count at all when we do this sum. And set B to split the difference. So we set B to this form, but this is a bit less. I'll let you understand this at home if you read why this comes to this. But I wanted to get this key ideas of how the W comes. Okay. Yeah, this is it. This is what I wanted to go through. Okay, shall we do a quiz? All right. Let's see. How do I exit full screen? Okay. Okay. Okay, so simply go to here to joinmyquiz.com and put the code. And again, please use your real name so we can keep track of participation in the class. Yeah. Okay, has everyone not joined? Okay, we have a few. Okay. So go to joinmyquiz.com and put this code. Okay, are we all ready? Shall we start? All right. So 3, 2, 1. What happens when you try to train a perceptron on non-linearly separable data?
Apparently people can't see the join code on Zoom.
Oh. Here, this join code. Yeah. Nice, congratulations. Nice. Multiple solutions are found, the training algorithm does not converge, an error will be returned, moves the data points to make them linearly separable. Yes, so can it be possible that multiple solutions are found with the perceptron? No, so it always returns one solution, one boundary. It's not a Bayesian method to capture a posterior over, to capture multiple model solutions. The training algorithm, let's say the third one, an error will be returned. Can it return an error? No, it always does those two update steps. It updates the W and updates the B, and it can never become, at worst, the boundary will be really off, but it will never return an error. Can it move the data points around to make such that they will become linearly separable?
No.
It doesn't do that. But why can't it do that? The perceptron algorithm per se does not move around the data points. It just tries to find the boundary. The data points, the setting is that these pluses and minuses are static, so you do not move them. Yeah. We'll see next time when we talk about kernel machines how we can lift these data points in a high dimensional space. And those kernel machines will turn these 2D data points into n-dimensional data points, which will become linearly separable. It won't be per se moved around, but they will be lifted in a high dimensional space at least once. And then we'll see that shortly, and with different kernels, so you can choose which kernel you apply. Sorry? Yeah, and if you lift to more dimensions, you'll get separability, linear separability, yes. Hopefully, at least in that high dimension, which would be super interesting to see. So this is the behavior. The training algorithm does not converge, which is correct. Okay, does it make sense? Okay, next question. Ready? 3, 2, 1. Regarding soft margin SVMs, mark all true statements below. Okay, before we go into the answers, do you remember what was the form and even what we're trying to do? So with the soft SVM, we were doing this. We were using slack variables, so to account for errors. So the setting was this. Let me show you the plot. So here, slack variables. So we were accounting, the soft margin was allowing errors. So even and even if the data was not linearly separable, it was still, yeah. So this was a setting of soft margin SVMs. Now let's go to our quiz. So yeah, interesting. So let's take them one by one. It will always find a solution even for non-linearly separating data. It is true. For soft margin SVMs, it will always find a solution even if the data is not linearly separable, because it can account for the slacks. It can account, yeah, with those. Which is not the case for the hard SVM. So the hard SVM, if the data is not linearly separable, it will not find a solution. Second one, it is more robust to outliers than hard SVM. Is it more robust to outliers than hard SVM?
Yeah.
Yeah? Why?
Because it can, well, if one is not going to make it not fail, and
Yeah.
our slack,
Exactly.
for those spots.
Exactly. So the outliers can be accounted for with the slack variable, and it will never fail. Also, it generally will never fail, the soft margin SVM. It can learn to separate more than two classes. Is that true or false? It's false. Yes, that's correct. So it's only binary classes. We're still in the binary setting. Optimization is hard. No direct solvers exist. Is that true or false? False. Yeah. How do we solve it? What are the solvers, or yeah, what's the paradigm, or how do we optimize it?
The gradient descent.
We can do gradient descent. Can we? It gets a bit tricky with the constraints, right?
Mm-hmm.
We can still do it. We can even. I think in theory, you can still do gradient descent if you. But we can do again. We can do those like quadratic programming. What I mentioned. We didn't go through. We can do quadratic programming. You can do and even analytical solutions, as we saw. We show in the second part, just now before the quiz. I showed you how you can solve it analytically with the KKT conditions. So you can even solve it analytically. You actually don't need to do an optimization even. So the whole thing is with the SVMs, you can get an analytical solution. So you don't need to do. You can use numerical solvers also, but you can also get it analytically, as I showed demonstrated in the lecture. Okay, 2 more questions. Ready? Next question. can you see the figure on your side on your phones?
Yeah.
Yeah. Okay. Because it doesn't show here. Oops.
What, I like the whole player responses.
Why's your kid no response? That would be hilarious.
Sorry. I want to know the responses. Let's see. So you have to find out, you circle outline, like make your circles around all the points that are support vectors. So make, if you think like you have 2 points and think one is a support vector, and do like this. Like, yeah. Okay. 10 more seconds. 9. 7 seconds left. Okay, let's see. Let's see. I see a few things. So can the whole line be a support vector? First of all, like a whole boundary? No. So you can only the support vectors are only data points. It's not an entire line like this. This is basically our separating line, and this is the bound. This is a boundary at 0. This is a boundary at +1, and it's a boundary at -1. So these are the lines cannot be support vectors. So for example, this person showed these two, which are on the lines. So those are support vectors. They lie on the dotted line. They are support vectors. What about the middle ones? What about these inside? Are they support vectors? We'll see shortly that they actually also are those inside. They at least for the support. I'll show. So these inside are also support vectors. They will contribute to the weight of your solution, because for these points inside, the slack variable is so for these points the slack variable is I think 1, and for this is between 0 and 1. It could be 0.5. The zeta is like 0.5, for example. So that means zeta equals 0. It means there's no they are outside this region, like a 0 or like but if it's 0.5, then they will contribute even these inside. Sorry.
Whenever black point is there, above that line.
This one.
+1 above +1. That +1 line is the black.
Oh, this. Oh.
That will also be support vector.
Yes. So these outliers will also be support vectors. So they will also contribute to the solution. They will contribute to, because by being support vectors, it means they contribute to the solution. So remember, the solution is given. So W equals the sum of alpha I, y I, x I. So for and there's only a few of the data points, that's the support vectors, for which alpha i's will be different from 0. Those will be the support vectors. There'll be just a few. So the solution will be given in terms of also of these outlier points, this one and this +1 here. So yes, I see. So these are not. So this is not correct. So these data points don't contribute at all. And we have some examples, but So I didn't go on purpose on this last 2 slides because it had the answer to the quiz, but here. So support vectors are points that lie on the margin boundaries, and in that case the slack variables are 0. They lie within the margin region. And the slack variable 0 is between 0 and 1. So this is for these ones in between. These will be right in between for within the margin region, and also lie on the wrong side of the hyperplane. So these ones on the outside lie on the wrong side, but they will contribute to the solution, to that W. Okay. So final question. Okay, and then we're finishing. Does it all make sense? Yeah. So I did not go on purpose because I had the answer to the quiz on that slide, but that's the last slide. So next question. Okay, final question. On this figure, why can the dotted line not be a feasible boundary for an SVM? What about a perceptron? Write some keywords. Just you can speak to your colleagues also. We can discuss. Let's start looking while the answers come in. So it doesn't have any points that lie on the line. Yeah. Well, so on the inner boundary, you don't need to have points. You need generally. So points might lie only on these outer ones, like on the dotted ones. So what I meant is that why can't the dotted line be like a feasible, the main line that equals 0 basically. But you don't need to have on that main line, on the main inner line, you don't need to have points that lie on it. So does it make sense? It does not maximize the distance of the maximum margin. Yes. So that dotted line is not maximizing the distance. So SVM is a maximum margin solution. Maximize the distance between to the closest points. Dotted line is not the optimal solution for the SVM. The line is fine for the perceptron. Yes. So the perceptron is fine with generally any lines, even if they're not maximum margin maximizing them. It does not have the greatest margin between data points. Same issue for perceptrons. So the margin is not maximized. Yes. It does not exist on the solid line. Too close to the positive. Yes. PCS will not maximize the margin. Dotted line can be a perceptron. It does not maximize the margin of perceptron. Because the margin could be improved by moving dotted line to the solid line, yes. However, it could be a feasible boundary for perceptron since the only requirement there is the data to be completely separated. Exactly. This is all. Correct. Margin is not maximized. Okay. So that's who's our leaderboard today. Okay, congratulations, Aaron, Matt, and Jacob. Okay, so that's the end of the class. I'll see you on Thursday, and we'll start kernel machines, I think, if I'm not mistaken, next time. So we'll extend this to, and we'll see how we can lift these points in multiple dimensions. Yeah.
Are you around tomorrow? I think that works. Was it 12? I'm available for like. Alright, see you.
Hi.
My name is Kalyan Sumasri. So I want to apply for TA positions in the next quarter for CSC 30.
Oh, hi. Yeah.
So I wanted to ask you if you can give me a preference in the application form.
I can do that. I can try that. Yeah.
So I wanted to let you know that I will be applying for CSC 30.
Yeah, sounds good. Like I think we'll generally be quite alright. Like we will have like a lot of TAs, like around 10 TAs in total. So but I don't know for sure. Like I can try. Send me an email, and I'll so I have your name.
Sure.
And
I'll drop my mail today.
Yeah, you drop an email. All right, great. Yeah. Have you taken the course in the past?
Python. Yes, in my bachelor's, but my bachelor's was in India.
Bachelor's in India, yeah, and you've done Python. Perfect. Great. I'll do that. Yeah, welcome.
Yeah, Professor.
Hi.
So, in that soft margin, the slack parameter again.
Yeah.
So it will be dependent on our data point, right?
On one data point?
No, all the data for each data point will be different, right?
Yes, exactly.
Yes.
So the slack is specific for each data point. Yeah.
So if our test data set comes, how do we know the slack for that?
Oh, you don't care about slack anymore at test time because you already have the solution. You already have the solution of W and beta
so
to give you the model.
Only comes in the optimization.
Only
not
the
in our
optimization. Yes.
Actual equation.
Exactly. So at test time you won't
You
need
only
the
find
slack.
margin
You don't
on
need.
this.
Yeah, you do the prediction. That simple prediction with the activation WX plus B
That's the margin.
times. That's it. And compare that if it's positive or negative. Yeah, you're welcome.